let's review for exam 2. So we're going to do a couple things here. We're going to review for exam 2. We're going to call that lecture 14. And then we're going to start chapter 6. That's going to be called lecture 15. Now, so I'm going to release 4 lecture 15 videos, so about an hour's worth of lecture 15 videos today. That's going to be kind of the introduction to the second law. Chapter 6 is really going to kind of come in 2 major components. So we'll get around half of it done today, and then we'll get the other half. I'll release videos on Thursday for the other half. Okay, but again, our focus here right now is to review for exam 2. Okay, let's talk about how it's going to work a little bit. Exam 2 is going to be Thursday, July 2nd. You'll have all day to do it, but once you get started, you'll have a time limit. And rules discussed on Canvas. So let's not Canvas. There's only one S in Canvas. Let's not tie up time here on these videos talking about logistics. I will post the rules and how the exam is going to work. It'll work very similar to exam 1. You'll have some timed questions, answer some identify the fundamental principle needed to solve the problem in a very short period of time, and then you'll go back and actually solve the problems. There'll be 4 questions, 4 problems, and it's going to come from, in the Changle and Bowles text, chapter 4 and 5. So that's basically first law for closed systems and first law for control volumes is going to be our focus here for exam 2. Okay, so again, logistically it's going to look very similar to exam 1, how I did exam 1. We're going to go ahead and do this one online. I'm going to work with my dean a little bit. Expect to do either the final or exam 3 on campus. We'll be prepared to do that, but we're kind of playing a few things by ear. Okay, if it looks, the biggest thing is just make sure that you're doing your own work here. If multiple people turn in verbatim copies of the same solutions, you will get zeros on those problems, if not the entire exam. You do it more than once and you will fail the class. I've done that. I don't have a lot of patience for that. These problems are complex enough that if you're working the problems on your own, you will come up with a unique solution. There will be differences between yours and anybody else's. So as long as you're doing what you're supposed to be doing, that really shouldn't be any worry at all whatsoever. Okay? If you have questions, ask me. It's easier to figure that out than it is to beg for forgiveness. So anyway, again, Thursday, July 2nd, you'll have all day to take it, but once you get started, there will be a time limit. Probably 2 hours, similar to what exam 1 was. Chapters 4 and 5, no unsteady flow. Right? I made that very clear in that last lecture, in lecture 13. That the unsteady flow topic will not appear on the exam. It's good to look at and understand, and kind of have an idea how we can use uniform flow to simplify those, but that's not going to show up on the exam. Okay? So chapters 4 and 5 up to unsteady flow. Let's talk about topics. What are we looking at here? Okay, well, we do need to be able to figure out properties. Right? So the focus is chapter 4 and 5. It's not necessarily, well, the exam essentially is, comprehensive. It's not that I intentionally make them comprehensive, it's just everything we do in this course builds on the stuff that we've already done. So inherently this class is comprehensive. So the exams end up being comprehensive. You still need to understand how to find properties. We know for R134A and water, our text has substantial tables for these. Now, if I have water remaining in the liquid phase, I could possibly use specific heat. With R134, I don't think you're ever going to use specific heats for R134, but possibly for water, but most likely if I can use tables, that's what I'm going to use for those. These, of course, as we saw in Chapter 3, you need two properties. We talked about how to use the property tables for water in R134, so hopefully you're starting to get really good at that. I was seriously not kidding when I said the first 100 times you use the property tables is a little rough, and then the next 400 to 500 times you get better at it. That's going to very much become true. Ideal gas does show up on this exam, specifically air, like the air we breathe. Could be nitrogen also, or oxygen, or carbon dioxide, or carbon monoxide. There's various gases. If it's water, there's situations you could treat water as an ideal gas, but I don't know why you would, because you got such really good property tables if you've got water in the gas, in the vapor phase. Okay, but if it's air or any of these other substances, we're probably just going to treat it as an ideal gas, meaning pressure times specific volume is equal to a gas constant times temperature. Use absolute pressure, use absolute temperature. And then, so that will relate pressure, volume, and temperature to one another. And if it's for ideal gases, so ideal gases continued, for ideal gas, H and U are functions of temperature. So where with water in R134, I would need two properties. If it's an ideal gas, I really just need temperature. So if I don't have temperature, I might try to use the ideal gas to see if I can get to temperature. Okay? So if I can get to temperature, with temperature in hand, then I can somehow quantify those U and H values. Okay? So let's see, what else we got? So as far as quantifying those properties, we could talk about specific heats. We introduced that concept in Chapter 4. Specific heat requires a constant phase. Right? So it requires a constant phase. So if I have, with that in mind, if I have an ideal gas, I can use specific heat to determine a change in internal energy. A change in internal energy is equal to the integral from the initial to the final temperature of C sub V dt. Now we normally don't do the integral. You could. It's actually just typically we can model it as a third order polynomial, and it's pretty easy to integrate. You have to go look up properties for C sub P and convert it to C sub V. It's not hard to do, but it's a lot more in depth than just simply saying, you know what, let's assume that C sub V is constant. We do need to use the average temperature to find C sub V at the average temperature. And if I assume the C sub V is constant, it comes out of the integral, then I'm just integrating dt from T1 to T2, and that just simply becomes delta T. So again, it's an approximation, but it's normally, and we've seen this in examples before, if I get a good average specific heat, it will give me a pretty good approximation for delta U. Don't just pull C sub V at room temperature. Some of you guys are doing that in your homework and you lost points. You'll lose at least that many, if not more, points on an exam problem. Don't pull the first C sub V value you come to. Go actually find your average temperature and then pull C sub V at the average temperature. Same thing if I need enthalpy. For whatever reason, we need enthalpy as we saw in Chapter 5 when we deal with control volumes. Delta H we can quantify with C sub P dt. And again, if I approximate that C sub P as constant at the average temperature, then I'm just left with the integral of dt, and that just becomes delta T. So delta T, C sub P average gives me a good approximation for delta H. Again, don't just pull the first C sub P value you find. Actually find the average temperature, look up C sub P at that average temperature, and that'll be okay. Again, requires constant phase. That's why I would suggest do not do this for R134. We use R134 because it tends to go through phase changes when we want it to. It goes from liquid to vapor. If you know it's in the vapor phase in both, both from state 1 to 2 and stays in the vapor phase, okay, maybe, but the problem is you don't have specific heats for R134 vapor. So your text really isn't going to help you there. You could do this for water, but again, I don't know why, because you've got such really easy to use superheated water vapor tables. I wouldn't even mess with this. But if it's air, carbon dioxide, carbon monoxide, nitrogen, things of that nature, this works actually quite well. Again, get a good average specific heat at the average temperature. Okay. If you have a solid or liquid, again, phase must remain constant. So if it's solid, it has to stay a solid, or if it's liquid, it has to stay a liquid. If the phase changes, then we got to do something else. We got to talk about the heat of fusion or heat of melting, or whatever the phase change is. We got to look at that property, incorporate that. It gets a lot more in depth, and we're not going to worry about the solid-liquid phase change in this course. Liquid to vapor, yes, we'll do that with water in R134, and that's what the property tables are for. But if I know I've got a solid remaining a solid, if I know I've got a liquid remaining a liquid, your text uses C sub P for solids and liquids. A lot of text will simply use C, the specific heat, because for solids and liquids, there's no difference between C sub P and C sub B. Right? For ideal gases, there is a difference. We talked about that in class, so let's not worry about the details here. If I need the change in enthalpy for a liquid, if it's flowing through a control volume, that's approximately C sub P delta T plus V delta P, specific volume times the change in pressure, or the change in pressure divided by the density. Either one gets you there. Okay, and that'll give you the change in enthalpy. Should you happen to need it for a solid staying in the solid phase or a liquid staying in the liquid phase. Probably don't need it for a solid, but you might need it for a liquid because it does flow sometimes. But again, requires a constant phase if you're going to use specific heat. Good for ideal gas. Okay if it's liquid staying liquid or solid staying solid. Probably not going to test you on this, just FYI. This definitely could show up. This may show up at some point, definitely in some homeworks. I don't know how to put it on the exam. There's just enough other stuff going on. Okay, what else? Properties, specific heats. Okay, let's talk about boundary work. One of the learning objectives for this course is be able to solve problems involving boundary work in compressible systems. So let's talk about boundary work. Typically, we're only going to encounter this in a closed system, although I guess you could have it in control volume in theory, but we normally aren't going to worry about it. It's normally going to show up in closed system where if the volume changes, if the volume changes, work occurs. The volume of the system is not going to change spontaneously. Something has to make the volume of that system change, right? If I've got a cup of water here, it's not just, the air in this cup is not just going to change spontaneously. Normally I ask if somebody's got a water bottle if they don't mind me using it. We'll do this, right? So if I change the volume of this system here, I have to do that with some work. I have to actually push that. I have to actually do something to that. And if I've got a system that is trying to expand into the surroundings, it's not going to do that spontaneously. There has to be forces inside pushing its way out. That manifests itself in terms of pressure. What we normally do is we compute what we call the boundary work, W sub B. And that's what we're going to pick up on the next video, is pick up on boundary work. Alright, where am I at? Yeah, we'll pick up on the next video with that.